These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. The nucleus of the atom contains the neutrons and the protons. And last time we talked about how almost all the mass of the atom is accounted for by the neutrons and the protons. And we saw that takes up almost none of the space. So almost all of the mass is put into this tiny little space. Now, what are the charges on the protons?
Positive.
Positive. So do protons attract each other or repel each other?
They repel each other.
They repel each other. But that means there's something that should really have bewildered us about that picture of the nucleus, because we've said that all of the protons are crammed together into a tiny little space. Well, why would they want to do that if they all have positive charges? That doesn't seem to make sense. It makes sense that the electrons would hang around in the outskirts of the atom close to the protons because they're attracted. But it doesn't seem to make sense that we can cram all of these protons that repel each other into this tiny little space. What's the solution to that? Well, there must be some other force that is counteracting the electrical repulsion between the protons. The electrical force is just one of the forces. There must be some other force that's countering that. And that's a force we've never had to talk about up to this point in the class. It's called the strong nuclear force. This is called the strong nuclear force. That's a logical name. It's called the nuclear force because it's operating between the particles inside the nucleus. And it has to be pretty strong to overcome this electrical repulsion and allow the protons to be crammed so close to each other in the nucleus. We haven't had to talk about the strong nuclear force earlier in the class. Earlier in the class, we've only talked about gravity and electromagnetism because the strong nuclear force is really only important inside the nucleus. So there's a strong nuclear force that's holding the nucleus together. By the way, last time we talked about radioactive decay, and we said that some nuclei are unstable. Well, one reason why a nucleus can be unstable is that sometimes the electrical repulsions overcome the strong nuclear attractions, and that's what causes the nucleus to change into something else. So the fact that there is all this electrical repulsion is one of the things that can cause the nucleus to be unstable if the electrical repulsions ultimately, in a particular nucleus, overcome the strong nuclear attractions. In a nucleus, therefore, the protons and the neutrons are all held together by that strong nuclear force. Let's say we take a nucleus and we disassemble it. We take a nucleus and we separate out all the protons and neutrons. We're taking the nucleus and then we're disassembling it into separate protons and neutrons. Well, this is not going to happen naturally. Remember, the protons are attracted to each other by that strong nuclear force. We're going to have to expend energy in order to separate those protons. So we should be putting in energy. In order to separate the protons and the neutrons, we're going to have to add this extra energy. This is what's called the binding energy, because that's what we have to overcome the binding of the protons and the neutrons to each other in the nucleus. Something we haven't talked about before, we've talked about a bunch of weird things that modern physics has discovered, but one of the weird things we haven't talked about is mass-energy equivalence, because that's mainly part of relativity. I don't think your course really covered relativity, but this is one aspect of relativity we do have to talk about here. One of the things that Einstein discovered as part of special relativity is mass-energy equivalence. That means that mass and energy are essentially equivalent to each other. Do you remember what the equation is that tells you how much energy you can get out of a certain mass?
E equals mc squared.
That's right. That's a very famous equation. Even though you haven't studied relativity, you've somehow bumped up across that equation. Well, I'm sure you've heard about E equals mc squared before, but maybe not everyone realizes that this is describing mass-energy equivalence. It's saying that we can take a certain mass and figure out the amount of energy that's equivalent to that, or the amount of energy that's equivalent to a certain mass. E stands for energy then. What would be the SI units for energy?
Joules.
Joules, that's right. However, a joule is oftentimes too big to be useful when you're working with subatomic particles. What's the unit of energy we often use for the nucleus?
Electron volt.
That's right, electron volts. We've talked about how that's confusing because a volt is a unit for potential,
Right.
but an electron volt is a unit for energy. And if you've been working through the recent homework, you probably had to do a lot of stuff with electron volts. The SI unit here is joules, but sometimes we're more interested in electron volts, or maybe mega electron volts, which is still a lot less than a joule. What would the M stand for?
The mass.
And the units for that would be?
Kilograms.
Kilograms. However, again, a kilogram is a much bigger mass than any subatomic particle. What's the unit that we oftentimes use for subatomic particles for the mass?
Nanometers.
Nanometers?
Nanometers, not meters. Micrograms.
Micrograms wouldn't be a terrible unit. The standard, well, not the standard unit, but the common unit for subatomic particles is, remember, U, or atomic mass units. U, or atomic mass units. After all, those are the units that we're using when we say that a proton has a mass of 1, and a neutron has a mass of 1, or that a helium nucleus has a mass of 4. These atomic mass units, or U. So oftentimes the unit for energy for subatomic particles is electron volts. And oftentimes the unit for mass is U. And while we're at it, what's the common unit that we use for charge for subatomic particles? We know that the SI unit for charge is coulombs, but for subatomic particles, oftentimes we just use E. I think we might have talked about this last time too. So all the units that are standard SI units are sometimes not that convenient for subatomic particles. So instead we might use electron volts for energy, U, this is a lowercase u, for mass, and E for elementary charge, even though the standard units are kilograms, coulombs, and joules. And what does C stand for?
Speed of light.
That's right. C is the speed of light in a vacuum. That's 3 times 10 to the 8th meters per second squared. No, that's just 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. Now, one thing to notice about C is that it's a pretty big number. 10 to the 8th is a pretty big number. And then if you square it, it's a really big number, 10 to the 16th. Well, that tells you that a small mass could potentially provide you with a lot of energy. A small mass could potentially provide you with a lot of energy. This is the reason why nuclear power has the potential to provide lots and lots of energy, because we can take a very small amount of mass and get a lot of energy out of it. So this is one reason why, if they could be built safely, nuclear power plants might be very useful, because they can get a lot of energy out of a very small mass. Whereas you might have had to do some homework problems where they compared that to how much energy you can get from a mass of coal. It takes a much bigger mass of coal to get a certain amount of energy than the same mass if you want to get the nuclear energy out using mass energy equivalence. And that's also why nuclear weapons can be so powerful, because even a small mass could potentially provide you with a lot of energy. All this time previously in the course, we've always been using this idea of conservation of mass. That is, whatever mass you started with is the same mass you ended up with. But now that we know about mass energy equivalence, we can't quite use that anymore. Instead of having conservation of mass, we have conservation of mass energy. That is, if you take the total amount of mass plus energy, so to speak, that should equal the final amount of mass plus energy. But so, for example, it's possible to gain more mass if you're adding energy. This equation shows us that it's actually possible to gain more mass if you're gaining energy, because the energy is equivalent to mass. Normally, it would seem that if you start with 6 kilograms, you have to end up with 6 kilograms, because it seems like mass can't just suddenly appear out of nowhere or disappear into nowhere. But now mass can appear out of nowhere if it's appearing out of energy. Well, that applies to this equation over here. We're taking the mass of the nucleus and we're adding energy. That means that the total mass on the right-hand side, well, should this mass be bigger or smaller than the mass of the nucleus?
Bigger.
Bigger, because it includes not just the mass of the nucleus, but the equivalent mass of this binding energy over here. So this mass should be bigger. And this mass should be smaller. because this bigger mass includes not just the original mass of the nucleus, but the binding energy, which could be cashed out into mass using E equals mc squared. Again, all this stuff in modern physics should seem pretty weird because it seems like we're getting mass out of nowhere, but it's not really coming out of nowhere, it's coming out of this energy. But you can see how this does seem weird. You would think that if you want to figure out the mass of the nucleus, you just add up the mass of the individual protons and neutrons. What this is saying is the mass of the nucleus is less than the mass of the individual protons and neutrons. This should strike us as pretty weird. Even though the nucleus is made out of protons and neutrons, the mass when the protons and neutrons are together is less than the mass when they're separate, because the mass has gone into this binding energy. And the difference between these is what's called the mass defect.